because of how the reaction works. Right? And so some of those reagents aren't quite as reactive as acids or bases, and so they are much more selective in how they react. So if we go through and look at this end reaction, you'll notice that we end up with two possible products. Right? In one case, atom X and atom Y are on opposite sides of the original double bond. Notice the stereochemistry just kind of pushes the R groups one direction or another. If they're on opposite sides, we might have said trans, but trans really only applies to double bonds. Well, there's no double bond. Right? So what we end up referring to it instead is an anti-addition. Okay? Trans being the adjective describing a noun, and then our anti-product is our anti-addition. The anti is in reference to the verb or the action. We're looking at an adverb. Okay? I know everybody laughed about that as we left, but that's what's going on with it. You run into the same issue with the other product. Our X and Y are on the same side of where our double bond originally was. So we might refer to it as cis, which again is technically wrong because there is no double bond. Okay, so we can refer to the action of making that product, and that is our syn addition. Okay, so you'll hear syn and anti additions pop up all over the place. Kind of be aware that sometimes those names can be misleading, and just because it is a syn addition doesn't mean that it looks like they're on the same side. Because if we take a look at the structure, what is special about the bond connecting the carbons with X and Y? It's a sigma bond. It can freely rotate. So we could look at a structure and say, oh, they look like they're in the trans alignment, but you would have to then backtrack to what it looked like when the reaction occurred to officially nail down syn or anti. Kind of makes sense? Okay. So, almost everything that we're looking at within chapter 12, and I think it's chapter 19, are involving alkenes or pi bonds reacting with cyclic transition states. Okay, and sometimes pushing it all the way to not just a cyclic transition state, a cyclic product comes out of it. Okay, so we get a lot of ring transition states. Yeah. So, alkenes, odd dual reactivity. Why are they odd in their dual reactivity? We've talked about this. When we look at the alkene, how do we expect it to react? A nucleophile. There are electrons. We would expect it to act as a nucleophile. However, the instant it acts as a nucleophile, what happens? You get a carbocation, in which case it acts as an electrophile. So alkenes kind of have this dual nature to them. They will first exclusively act as nucleophiles, but then depending on stability and the reactivity of the reagents they're working with, they may very rapidly react as electrophiles. Okay, so you can get kind of a mixture. When we look at chapter 11, it was looking at our Lewis base, which classified it acting as a Bronsted-Lowry base. Okay. Now we're shifting to it acting exclusively as a nucleophile. It's reacting with anything other than a hydrogen ion. Okay, so our first reagent that pops up, carbenes. Okay. Carbenes are interesting because what is their characteristic? They are both electrophilic and nucleophilic. They have the same dual nature that your alkene does. Do I have nice pictures here? I'm going to guess I don't have nice pictures here. I do not. Two common reagents, diazomethane and your trihalomethane compounds. Okay? So let's break down our trihalomethane, because you guys can probably come up with a nomenclature for that one. What does a trihalomethane look like? Trihalo, 3 halogens on a single carbon. So in this case, I've got a tribromomethane. We look at that, we said the characteristic is that it is electrophilic and nucleophilic. Does anybody see how that structure can act as an electrophile? Bromine could act as a leaving group, which would then make that carbon electrophilic. So yeah, that makes sense. Where is it acting as a nucleophile? Okay. It can't really act as a nucleophile yet, but if it goes through a primer reaction, that primer reaction being an acid-base reaction, I react this with a strong base, the base can come in, remove the hydrogen, the electrons in that bond go to the carbon, we would end up forming the carbanion with a negative charge. We still have a really good leaving group in our bromine. If one of those bromines just left, we would end up with what charge would that carbon now be? Neutral, which is a bit bizarre. Okay, it started negative. I have something leave. We would expect it to become positive. Well, it is becoming more positive. It's going from negative to neutral. Okay. What hybridization is that carbon? sp2. There's still 3 groups of electrons around it. Okay. The electrons, the lone pair on that carbon, is our now nucleophile source. Where's the electrophile? May help if I do a subtle rotation here. If it is sp2 hybridized, what is left unhybridized? A p orbital with no electrons in it. We now have a place to dump electrons. There's our electrophile. So what can happen? We can take our now active nucleophile electrophile species. Our alkene will still act as a nucleophile first. Electrons come out, react with the carbon, but now that carbon, having a lone pair of electrons, can immediately share those electrons back, the result being we end up with a 3-membered ring. Okay. And yes, we may be saying that's bad, that's high energy. Yeah, that's actually one of the reasons why we might make it. Okay. We now have a structure that is exceptionally reactive. We can get a little bit more energy out of this. Okay. Why would we bother to go through and make the 3-membered ring if that is so bad? Well, how stable is the carbene? Okay, not very stable at all. So even though we may be making an unstable 3-membered ring, we're trading off, we're still going lower in energy because that carbene is exceptionally reactive. Okay. Some other features that might become important on this. Okay. We still have those 4 bonds, right, hanging off the carbon. Where's the hydrogen? I like what you said. Say that again a little louder.
In the back?
What do you mean in the back?
Be away from us on the left-hand side.
If you're saying that's away from us, where's the R group? Just the R, not R1 or R2. It's now coming towards us as a wedge. Where's R prime? And R double prime? Away from us. According to the mechanism that we just looked at, would we ever see R double prime on the same side as R? Why not? There's no, I haven't specified what the electrons are on those, so we can't say anything about too many electrons.
There's no assumed sign for rotation.
To get R double prime and R prime on the same side of that ring, what has to happen? You have to rotate about that bond. Well, in the ring structure, can we rotate? No. Well, maybe we could rotate in the starting structure. In the starting structure, we have a double bond. We have the alkene. It can't do the rotation either. So this reaction is happening where we are breaking the pi bond, forming one sigma bond, forming a second single bond, all at the exact same instant. The mechanism is known as concerted. okay, or simultaneous, kind of like our SN2. Because of that, whatever stereochemistry we have with our alkene is the stereochemistry that we end with our product. Okay. How many carbenes do we end up with as a possible product? Why 2? This is showing the carbene reacting from the top. It could just as easily react from the bottom. So we still get 2 products, but in both those cases, R and R double prime are still on opposite sides. Okay, they will never line up on the same side. Kind of makes sense? Okay. The other reagent that you could potentially see in all of this, we erase everything, is something known as diazomethane, which is a little bit tricky. Anybody know what azo means? Nitrogen. So we have 2 nitrogens bound to a methane to fix out our Lewis structure. We would end up with something like this. Does that nitrogen want to be positive? No. So what does it end up doing? Trying to steal electrons. It ends up stealing so much electrons that what ends up happening? That hydrogen becomes exceptionally acidic, and we end up forming our active structure. Okay? And by exceptionally acidic, I mean really, really exceptionally acidic. Okay? So that what we end up seeing is something more along these lines. And we end up with the neutral structure. We have a negative charge on our terminal nitrogen, positive charge on the nitrogen. Does the nitrogen want to be positive? No, so what can happen? It could take electrons. Okay, but then it has too many electrons, so what happens? Okay, then go back to our carbon, and we end up drawing what did we draw? Same thing, I'll accept that answer, and resonance. They're resonance structures of each other. Interesting feature within that. What happened to the charge on the central nitrogen? It doesn't go away. What does that mean? It is still exceptionally unstable. Okay? It is so unstable that it is frantically trying to leave the structure. To do that, what has to happen? It must steal electrons from the carbon, resulting in nitrogen gas and that awkward thing, sure, our carbene. Okay? This reaction is exceptionally dangerous. I've come in one case where I thought I was going to go through and do this synthesis or do a reaction involving diazomethane, and I was very quickly told by my professor there was no way I was allowed to touch that. Okay. The one person that I'm aware of that has gone through and done this reaction has lost fingers, has some stubs from this very reaction. Nitrogen is exceptionally stable on its own. It really wants to break off that structure. So that is a massively energetic bond. Okay. How can we get that nitrogen to pop off? If there's a fracture in the glass, like you know when you scratch glass, there's that little line you can see. That little crack is enough to cause nitrogen to break off. Okay. And I don't mean the action of making the line. I mean, here's the diazomethane in a container that has a line drawn in it. That is enough to cause it to ignite. Okay? And it will explode very, very violently. Okay? So not a particularly fun reagent. Okay? You could see some use to it because you're effectively transferring a carbon across, which can be very helpful for those of you interested in drugs. Okay? We'll leave it at that. Okay? So what can happen? This can now react with our double bond, same general mechanism as we saw with the last one. The big difference is that the end result, we don't have the dihalide, we just have a single carbon. It's still happening in a concerted mechanism, so if I make that R double prime wedged. What is the R prime? Must be dashed. Which atom is wedged on the left side, hydrogen or the R group? The hydrogen then must be wedged, and the other one's dashed. Our stereochemistry must maintain the same. We still have the potential for two products because alkenes. Sometimes stuff happens. Yes?
The diazomethane, while it still has all three hydrogens, is that a liquid or a solid?
Good question on the phase. I don't know. I'm fairly certain it's almost all gas phase
Oh,
in the reaction. Again, I haven't worked with it, so I don't know. It's fun to talk about because it's neat and explosive, but that's about it. You probably won't ever synthetically get to use it. As another comment, we talked about scoring glassware. You notice when we jointed our glassware together, what did you see in the neck of where those joints came together?
Frosted.
It was frosted. That frosting is enough to cause it to ignite. To actually use the material, you actually have to use unfrosted glassware because the frosting will actually cause it to ignite as well.
So what did they even use diazomethane for?
To do this,
Oh.
to attach carbons to structures. Yeah. We just try and come up with safer ways to do it. And there are other methods doing ultimately the same thing. Okay. One of the reasons why I bring it up is for the next sequence of slides, which I'm kind of going to have to sneak over. That looks familiar? Okay, that is our citric acid or our Krebs cycle. If we look all the way up in this very first step, our pyruvate dehydrogenase, anybody know important coenzyme? Thiamine. Okay, thiamine is a critical molecule for that reaction. Okay, you can see another version of it, TPP. I love biochemistry for this. They don't actually show you structures. They just give you names and say, oh, it happens. Okay. So thiamine's really critical to start converting pyruvate across to the acetyl-CoA, okay, which is important for a lot of different mechanisms. Okay. Why is thiamine really cool? Well, if we take a look at that reagent up there, what do we have? We have our trihalomethane with a strong base. Okay. We can react that, and we do a carbene reaction. Well, what is thiamine? Take a look at thiamine. There's our carbon. That hydrogen can be removed. What happens if I remove that hydrogen? What charge would the carbon become? Negative. What charge is that nitrogen? Formally positive because it has 4 bonds. Does it want to be positive? What can it do? It can steal the electrons from the carbon, and we have at that carbon position a carbene. Okay. Thiamine, as a vitamin, is a carbene. One and the same thing. Okay? So if for some reason you decide to take biochem with me, I kind of hate to tell you this, I'll probably tell you not to, but you're more than welcome to take biochem with me. We end up going through a lot of structures and referencing back to organic chemistry because biochemistry is organic, okay, regardless of what any teacher tells you. Okay? You can look at the big, long, nasty mechanism. Believe it or not, second semester you get tons of that. I only show it up here because we get thiamine acting as our nucleophile and very quickly later as kind of a pseudo-electrophile, okay, accepting electrons backwards, which facilitates the whole big reaction. And I think, do we see the, yeah, and we see the kickoff of our CO2 as well. Okay, so kind of neat. Don't stress. That's about it. Okay, so that's our carbenes. So alkenes is nucleophiles. This still gets back to our 3-membered rings. Okay, I do apologize. The order on the slides is a little bit messed up because this guy right down there does not form a 3-membered ring. Okay, and we will see that a little bit later. So we'll just put an X through it because I've changed the title. Okay, those of you in lab can help me out with this. What happens is the very first step for all of these reactions or reagents. What does your alkene act as? A nucleophile. What do we need to find? An electrophile. Okay. Turns out we end up seeing bromine act as an electrophile, which may seem a bit odd because what do we typically see bromine act as? A nucleophile. Okay. Elemental bromine has a 0 charge, so it is not going to act as a nucleophile. if we get electrons close enough to one side of that molecule, the molecule polarizes, and we can eject bromide as a great leaving group. So in all of these cases, what we're ultimately reacting this with is bromine positive. Okay? Not a particularly easy structure to get. We can really only get it from bromine being bound to a very electronegative element. Okay? Like in this case, bromine. The result is that we would have that positive bromine go where? To the double bond. Which carbon of the double bond? The least substituted position. Think back to the acid-base chemistry that we did. Where did the hydrogen go? The least substituted position, because it's positively charged. If we put another positively charged atom on the structure, where is it going to go first? The most negative position, which is the least substituted. The chemistry is identical to chapter 11. Markovnikov, stupid. Because Markovnikov can only apply to hydrogen ions, the acid-base chemistry. If we focus on the resonance of where our more stable negatives and positives fall, the chemistry falls out of it. There is no need to memorize some dumb rule and some long dead person. So we could put the bromine on there, but then what happens to our other carbon? It would be positively charged. Okay? This is where chemistry becomes a bit interesting. We might assume that this is our valid mechanism, and we would go through and look at our possible products out of this, assuming that intermediate. And what we later found was that that intermediate, we have direct evidence, does not exist. Okay? Something about that doesn't work. And what it ultimately comes down to is that if we shift away from this being a ring, okay, what would we expect happens at this point? Just,
Oh, the bromine will.
we could have a nucleophile come in, yeah, keep going. What do we have connecting those? A sigma bond. In theory, a sigma bond should be able to rotate, and we should get a whole bunch of different products coming out of this. It turns out we do not get those products. The sigma bond never rotates. Okay? The only way the sigma bond never rotates is something must prevent it from rotating. How do we prevent sigma bonds from rotating? Make them a pi bond. We just lost the pi bond, so that one's out. Ring. The only other atom that can make this close as a ring would be an atom with electrons. Where are their electrons? On the bromine that was just attached. And what we end up getting is, instead of just having the bromine, I need to clean up some arrows here. Our double bond coming up and attacking, we'd break off our bromine, and then a lone pair immediately comes down as well. And we end up forming this goofy little structure. We now have our ring structure that prevents rotation about a theoretical sigma bond. Okay? And that means we're now locked into this conformation, and whatever stereochemistry then is a repercussion thereof. Since we're in a ring already, we didn't get rotation, that's why I had to erase that ring. Okay? How many products do we have at this stage, if we assume this is a final product? 2. The bromine can attack from the top or from the bottom, or be attacked by the alkene from the top or the bottom. So there are 2 products at this stage. Okay? And we could specify that by including some wedges. If I made that bond wedge, what happens to the methyl group? Must be dashed. What happens to the other bromine bond? Must also become wedged. Why can it not be dashed? Okay. If the fleshy part in my hand there is the bromine, how can I connect the points of my iPad like that without doing some really weird geometries? As soon as in fact, I was trying to keep my hand above it. Okay. As soon as I have those bonds, to get one bond going down and the other bond, what naturally happens? They're now both going down. I can't possibly align my hand in such a way where one bond can be wedged and one bond can be dashed. They must be on the same side. Why? It's a feature of 3-membered rings. Okay. What else is an issue with the structure I've got drawn? Bromine is formally positive. Does bromine want to be positive? No. So we have an exceptionally good leaving group at this point. Okay? And we have two potential positions that that leaving group could leave from. So this is now our official substrate, but now we have two locations. Okay? Which location would the bromine prefer to take electrons from? The tertiary position, because more stable carbocation. Okay? And this will become relevant when we move into epoxides. With a great leaving group, we favor the next step, or the bond breaking, happening at the most substituted position. But you have to have a good leaving group. Okay? So that bromine wants to break the bond to get us to that carbocation, but we can't form the carbocation. Something has to come in and help that bond break. What needs to come in? A nucleophile. The nucleophile can now come in and cause that bond to break. If we draw out the product, I've got a bromine there. I have my new purple nucleophile out here. Wedges and dashes, where are they? Why does the nucleophile need to be dashed? Okay, this is a bit weird. We're still doing a backside attack on that bond, okay, even though we're attacking the most substituted position, okay, which seems to be kind of counter. We're doing kind of an SN1, SN2 all at the same time. Okay, we still have to do a backside attack, which then means the nucleophile becomes dashed. What happens to the methyl? It's going to get forced up into the wedged position, and our bromine, still wedged was a good phrase. What do you mean by still wedged? I don't quite accept that. Did we do any chemistry there? No. That's why it's still wedged. Nothing happened at that position. Everything happened somewhere else, so I cannot change the bond arrangement. Okay? Kind of makes sense? What is the arrangement of our bromine and our nucleophile? They are anti to each other. We have an anti-addition reaction. Why do we have the anti-addition? Largely because the bromine prevents the syn addition, okay, from our bromonium ion. Kind of makes sense? You'll notice that I went through and wrote nuke, even though several of you shouted out other potential nucleophiles. Okay, one of your possibilities was bromide. When is bromide a potential nucleophile? Start with Br2. Bromide is floating around. So there's your nucleophile. When we move to the second example, do I still have bromide floating around? Yes. And yet, when I move to that example, what product do I end up getting? So here, let me clear everything. Can I clear everything? Okay, plus an enantiomer. And the next one, what's the product I get? I end up with OH, technically plus our enantiomer. Why? What was the nucleophile in that case? First case, our nucleophile was bromide. In the second case, our nucleophile was water. Okay. Which is the better nucleophile, bromide or water? Bromide, because it's negatively charged. It's larger. It's more polarizable. Everything about bromide screams it being the better nucleophile. How on earth do I get water as the crappier nucleophile to attack? It's a concentration issue. There's more water present. Because there's more water present, water can outcompete the bromide from coming in to do the backside attack. Okay, that's it. Well, that's obvious because when we look at the arrangement of the reagents here, it very clearly says that water's there in a vast excess, right? Everybody see that, those words, really big concentration? Yeah, unfortunately it doesn't show up, it becomes implied in the equation, okay? That's all I got for you, okay? We can limit the presence of bromide to help force that reaction. As soon as you see water showing up, you should be thinking you're going through and putting the bromine in the OH on. You do go through an extra step because as water acts as a nucleophile, you will form a positively charged oxygen as an intermediate. You can do an acid-base reaction, ditch the hydrogen to get you the alcohol. Okay, there was a question there. And there's a funny face, I'll come back to that.
Why did the reaction with MBR, or MBR, donated its bromine, had the water, too, but we had more water.
Yep. So those of you in lab, when we went through and did the addition lab, we had a ton of water present. Why? We're trying to force this addition. We don't want a bromide coming in and doing our other product, okay? Or getting a different product in it. Okay? So we up the concentration of our water. Okay? There are a couple of funny faces when I mentioned the intermediate of our water attacking. I believe. Do I need to show that? I'm actually seeing heads shaking no. So if you want to see that, talk to me after class. Next one, what happens? What's our nucleophile? Admittedly, there's a typo that might make it a little more confusing. It's supposed to be a capital R. We take an alcohol, any alcohol, you can then put on bromine in an OR group. Okay? Why would you do that? If we add water, we now have acid-base characteristics from our alcohol. If we add it under an alcohol as our nucleophile, do we have an alcohol as a product? No, we have an ether. What is the reactivity of ethers? Virtually nothing. Okay? So that can limit later reactivity by putting it on in the form of an ether as opposed to a full alcohol. Okay? So you can almost see it protecting that functionality. Okay? Questions about those three? Okay. I have a better picture for this a little bit later, but let's take a real quick moment. Look at that last one. Have we seen diatomic molecules show up before? Yeah, Br2 just did that, right? So we could have H, okay, and we could have the double bond try and come in and attack that H, right? Our electrons would polarize, and we might expect something along these lines where we have the H, whoops, it's supposed to be an H, and that positive, and you say, okay, well the H then shares down, and we form this structure. And I'm hearing some head shaking no. What's the issue with that structure? 2 bonds to hydrogen. We have exceeded hydrogen's octet. Hydrogen cannot possibly share back to that positive charge. Okay? So that step of the mechanism doesn't work. Take it a step further. We'd end up with hydride as a possible product. In the other case, we had bromide. Bromide's fine. With that simple nucleophilic attack, we'd have hydride. Is hydride stable? No. So nothing about what I've shown here is valid. Okay, so something else has to happen to force this reaction to occur, and this is largely because hydrogen is too small to stabilize any of the intermediates. So what ends up happening instead is we have to add a catalyst. Notice that we're adding platinum or palladium, okay, or rainy nickel. There's a variety of metal catalysts that will do this. What will the catalyst do? What do metals tend to do? Share electrons. So where are their electrons? The alkene has electrons. Hydrogen has electrons. Diatomic hydrogen. And so what will end up happening is that both of those will coordinate to the surface of the metal, and the metal will coordinate the transfer of hydrogens to the double bond. Okay? But it can only coordinate the transfer of hydrogens to the double bond on The side making contact with the metal, exactly right. So that when we draw out the product, if I tried to draw on my hydrogens, what would the arrangement of those hydrogens be? Both wedged or both dashed. If that's the case, what happened to that methyl group? Whoops, I didn't draw that right. That's what happens when you're talking, right? So both wedged. The methyl must be dashed. Is that relevant for this particular drawing? No, why not? There's no stereocenter, so I'm not concerned about it. Are there cases where I could generate a stereocenter product? Yes. Okay. So our big difference when we're adding our hydrogen across is that we end up doing the syn addition. When did we do the syn addition? When we had small, tiny, unreactive things. Okay. When we have big things like bromine, we can go through and do the, we'll be forced to go through and do the anti-addition. Okay? Questions on those? I know, we're going through this really fast. So more to go through really fast. Okay? I'm going to change the focus around. I want to look at mercury, not the first one. So if we take a look at mercury first. Oh, I did change the order. Take a look at that mercury reagent. What do you see? Metal, okay. It's got lone pairs. We run into issues when we look at octets. Why do we run into issues with octets? What's that?
Mercury only has 3.
There's another issue. It's not so much that mercury only has 3. When do we look at octets and the octet rule? When we're in the first and second row. Where's mercury? Way down there. Located in the transition metals. What happens when we move into the transition metals? Our charges go hectic. What else? Why do their charges go hectic? Why are they sharing electrons even freely? Where are those electrons located when we move into the transition metals? The d orbitals. The d orbitals open up a crap ton of chemistry that pretty much makes organic look like nothing. Okay? Mercury here can do all sorts of weird stuff. Okay? Not the least of which, it has a lone pair of electrons that can potentially react. The next part, what type of bond do we have between mercury and oxygen? An ionic bond, which means really what's happening? It should break, and how should it break? Oxygen should take the electrons, and the mercury becomes formally positive. What is now special about that mercury? It's electrophilic because electrophilic is because it has the positive charge. And because it has a lone pair, it's nucleophilic. What happens when we take a mercury atom or take any atom that is both electrophilic and nucleophilic and we react it with an alkene? Stuff. You form a 3-membered ring. Avoid dealing with the charges on it. It's a mess. It's probably not something that's worth dealing with. Okay. Just realize that mercury can accept electrons from the mercury acetate, and it has the ability to donate electrons. So then when it goes down here, what happens? The double bond reacts with the mercury, with our mercury acetate, so sometimes you'll see it written as this, which then kicks out a leaving group. but then the lone pair on the mercury can share back. And you end up forming that intermediate known as, I see you, with the bromine, it was the bromonium ion. What do we end up with here? I left out the C. Mercuronium ion. It's the same general idea. Okay. If we added stereochemistry to this, if one of those bonds was wedged, what's the other one? Also wedged. Okay, Troy, there was a hand? Oh, with the wedges now? Yeah. So we do have to watch out for that. That ring is happening on one side of the structure. Okay. Deciding how important that is ultimately going to be pushing it all the way out to the end of the result to see what happens. Okay. So we will have the top product and the bottom product because we're reacting both sides because it's an alkene. Okay. Now what happens? Okay, well, if we look at the rest of this reagent, so number one, we see 1, 2. Okay, what does the 1, 2 mean? Steps. Okay, so we have a first step and a second step. So this is actually getting broken into multiple steps as we go through the reaction. Okay, what else is in the first step? And oxygen. And what does that oxygen have? Electrons, making it a nucleophile. When we kick out the acetate, we don't expect the acetate to act as a nucleophile because resonance. And hopefully you said that because you knew it was resonance and not just because I said because. Okay. The acetate ion has resonance, which prevents it from acting as a decent nucleophile. This is where the solvent, okay, in that reaction can come in and act as a nucleophile. It can either be water, in which case we'll be putting on an alcohol, or it can be an alcohol, in which case we end up with an ether functional group. Okay. I skipped the acid-base step on the last one, so I won't skip it here. Okay. Where does our nucleophilic oxygen come in? It needs to come in from the backside, so in this case it's going to be a dash. A dash where? Our most substituted carbon on the right or our least substituted carbon on the left? Do we have a good leaving group? Does mercury want to be positive? No. Okay. Next thing we could think about, when mercury first came in as the electrophile, just like our hydrogen, just like our bromine. Okay. The mercury is acting as our positive, which means the positive should go to which carbon? Our positive goes to the least substituted. Comes back to resonance. Mercury is acting as a positive. It should be going to the least substituted because that generates the more stable anion, negative to positive. Okay. That means when we have water come in, it's going to attack the central carbon, or in this case our more substituted, and we end up forming our mercury out here. Whoops, forgot to show the electron shuttle over. Stereochemistry. The mercury should be shown as wedged and our OH should be shown as dashed just because of how the reaction occurs. The oxygen would be formally positive. Oxygen does not want to be positive, so what happens? Something basic comes along and pulls the hydrogen off, What is something basic in solution? I don't know, how about another water molecule? Can pull that off, and we would end up with the final product-ish, or certainly actually true, our final product of step 1. Okay. This is the final product of our step 1. Our mercury is attached, and we have ROH. Okay. Why this becomes a bit dicey is that how often have you seen mercury bound to a final structure? Never. That's because it's not something we want to keep. Okay. Mercury is exceptionally toxic for this reason. We need to somehow get it off of the structure. Okay. What is the mercury going to want to do in this case? Okay. It needs to somehow get ejected from the structure, and this is not an easy mechanism to worry about, so you typically don't see it discussed. When we move to this next structure, we add sodium borohydride. What is sodium borohydride reactive as? We have sodium ion, and we have BH4 minus, right? Where's the negative charge in BH4? If we go through and calculate formal charge, we find it is found on the boron, and almost everyone says, oh, the boron's negative. No. Interestingly enough, sodium borohydride shuttles that electron to hydrogen. But then we'd have H minus. You can't have H minus, can we? Why can we have H minus? Guess what the electronegativity difference is between boron and hydrogen? Boron is actually less electronegative than hydrogen. Meaning when we look at that bond characteristic between the boron and the hydrogen, where are those electrons spending most of their time? On the hydrogen. Sodium borohydride acts as an H minus supplier, a hydride supplier. Okay. Taking a step further, it's not just a hydride, it is a nucleophilic hydride, which become important in second semester. Okay. This is not a basic hydride. It's actually really good as a nucleophile. What can end up happening? Through a sequence of nasty mechanistic steps that you really, really don't want to ask about. The end result is that we end up adding H and OH across the double bond. Okay. Interesting question there. Where is the hydrogen relative to the OH? We end up losing track of where it appears or disappears. Okay? And so the stereochemistry becomes kind of a moot point. And we only reference the OH and the hydrogen being added across the double bond and their appropriate regiochemistry. The regiochemistry being the hydrogen goes to the least substituted and the OH goes to the most substituted. And we keep our focus on that. Okay? So it ends up being a big mix of products coming out of that. Okay? And that ultimately is coming back to the chemistry of boron, which we'll see in a little bit in a slightly different form. Okay? Anybody have any issues with all of that mechanistic step?
What happens to the other acetate?
The other acetate will eventually hook back up with the mercury, and we kind of regenerate our mercury catalyst officially in this reaction. No issue with that? You saw everything you wrote, right? You were all excited and like, yep, I get it. Perfect, beautiful, easy, right? What's the product? We'll call this one purple. I just do this. What do I get? Where does the H go? The least substituted position. Where does the OH go? Most substituted position. What is the difference in our products? Is there stereochemistry here officially? No. What is the difference between our products? There isn't. What the F? Seriously? We just talk about all those stupid arrows and mercury doing all sorts of crazy, nasty stuff, and we've already produced that product before. Why the hell do we bother to deal with mercury, considering that it is stupidly toxic? Why do we use mercury instead of just doing acid and water with an alkene? It's actually not faster. 2 steps, you increase the odds of losing product. Strong acid, sure, but we've dealt with strong acids all the time.
Is it because you can reuse the mercury?
What is the first product formed when we do it with H plus and water? What was that? Say that louder. What's the issue with carbocations? It is unstable and it can do what? Rearrange. Did we draw a carbocation with the mercury? No. Why do we use the mercury reagent? No rearrangements. That's the only reason. So if there's no chance for a rearrangement, don't use mercury. If there's a chance for a rearrangement, you need to use mercury. Okay? That is a dangerous question to ask, and we'll see this pop up with using H plus and water, the mercury and borohydride, and the borane and the peroxide. All 3 of those answers will show up as a multiple choice answer, and you need to know why each of them makes sense over the other. Okay? The dangerous one, H plus and water versus the mercury reagent, because they produce the exact same product. The issue comes into play with rearrangements. Okay? So if you see both of those show up in an answer, that's a red flag that there is a high likelihood that your structure could rearrange. Okay? And you have to decide, did it rearrange? If yes, then you need H plus and water. No rearrangement, it needs to be the mercury. Okay? If there is a rearrangement, you need to be using H plus and water, if there's the potential for one. Or if you look at your product, so you'll get a reaction, and you'll say, did a rearrangement occur? If yes, it has to be with water.
Oh, okay.
If no, it has to be with mercury.
No other could.
Yeah, it's not whether it could, it's whether did it happen or not. Because if you see those 3 answers as a multiple choice, you have to look at what they gave you, and what they gave you will likely be a reactant and a product. And you have to decide what reagent best fits. Okay. If you see a rearrangement, it has to be water. Okay. Because it's not going to rearrange if it's mercury.
So this carbocation, that wouldn't rearrange though.
So there's no chance for a carbocation rearrangement here. So you would never see a multiple or exam question say which reagent do you use, H plus or mercury? Because both of them are going to get you that same answer. So it only comes into play if there's a rearrangement possibility, and that's when you see both reagents show up. Okay. So the next one, our borane, BH3. What's going on with BH3? Well, we look at its Lewis structure, what do we end up seeing? Trigonal planar and hybridization? sp2. There's no lone pair of electrons. We have sp2, which means we have an open p orbital. Borane will act as an electrophile. Nucleophile is the opposite, which means what happens? Our alkene can react with our borane to form a bond with the boron. Okay? Don't draw this quite yet. Where would I predict to show the boron? Left carbon, least substituted, or right most substituted? Why the least substituted? Whoops, that's an eraser. Think back to our resonance Think back to our resonance structures. Where's the negative charge more stable? On the least substituted position, what does the borane act as? A positive. Okay, it's acting as an electrophile, which means the borane should connect to the negative carbon. So identifying your positives and negatives can set up the chemistry. And what would be at the other carbon? A partial or an official positive. Okay. What's the issue with the structure I've got drawn now? Boron would be negative. Does boron want to be negative? No. So it's freaking out right now because of that extra electron density. Same thing it did, whoops, I already erased it, with our sodium borohydride. It is immediately trying to get rid of electrons. What's the only thing that can hold electrons in that structure? It's either the hydrides or the carbon. If it's the carbon, nothing happens. So it's now our hydrides. How stable are our hydrides? Not stable at all. So if that hydrogen then takes those electrons, it can't free float off into solution because it is that incredibly unstable. So what does it end up doing? It immediately attacks the carbocation. So the net result of this reaction is actually our electrons from our hydrogen immediately coming down and hooking up with our positive carbon. The result out of this is we end up with our hydrogen, which I know Smart would flip out of that question or that drawing right now, but let's be happy with it. We end up adding the boron and the hydrogen across the double bond. Stereochemistry. They need to be aimed the same direction. Okay, officially there's no stereochemistry in this structure, but we're trying to imply what's happening if we needed to worry about it. They would have to be added on the same side. Why the same side? It's a concerted step. Even if it wasn't a concerted step and for an instant we formed that carbocation, the hydride gets kicked off and immediately attacks the carbocation faster than we can do a sigma bond rotation. That means we get what type of an addition? A syn addition. Remember when we talked about our anti versus our syn? When they were big molecules, we had anti. When they're small molecules, boron and hydrogen, we get a syn addition. It has to be happening at the same time. Okay? This is the primary reason why I hate or Markovnikov nomenclature. Where does the hydrogen go according to that stupid name I can't remember? Markovnikov. The least substituted. Where did the hydrogen go? I would argue it didn't. Because what is Markovnikov looking at? The hydrogen ion. Is this a hydrogen ion? No, it's hydride. The instant you change the charge, Markovnikov's rule becomes meaningless. If you ignore his rule and focus on the charges, everything matches. There is no anti this or positive that. They just match. This is where positive negative becomes super, super important. Okay? We now have this structure with the boron attached. Okay? What can happen now? Well, this was a two-step reaction. Step one, I had BH3, did it, THF is a solvent. Okay? How do you know it's a solvent? Experience, you just have to know. THF is very typically used as a solvent. Right? It's what initiates this reaction. So there's nothing left in step one. What I need now is step two. Okay? What happens in step two? Okay. Did you say something weird? Good call. Something weird is a perfectly valid answer for what happens in step two. It's a big, nasty, long mechanism, which is on our next slide. What I prefer to go through and do is actually flip this structure over. I just need to get the boron a little more accessible. Okay. This is not the mechanism, okay, but it at least gets in the ballpark of what's happening within the stereochemistry. What does boron act as? An electrophile. It needs electrons. Where do we have electrons? We do have the potential for the hydroxide, but then nothing else can really happen. So we'll bring in the peroxide, H2O2. I can take electrons and donate them to the boron, but then boron has negative charge, so too many electrons, what can it do? Could theoretically just give off the hydrogen. Turns out we'll end up swapping all of those hydrogens out for carbon structures. We'll shuttle the carbon bond over to the oxygen. But then what happens to the oxygen? It succeeded its octet. And we get this neat little reaction happening. Okay, so there's our hydrogen. We'd end up having our OH now attached. The rest of the structure comes off as BOH. And again, officially we wouldn't have hydrogens there. Those would end up all getting swapped out for oxygens. Last question. How did the OH come in? Wedge or dash? This is one you do unfortunately need to know. Okay. It's a direct one-for-one transfer across with our peroxide. Okay. For it to be dashed, that OH needs to be wrapped around to the back side of that bond. Because it's all happening in the exact same instant, it stays wedged. The end result, beginning to end, when we use the borane reagent, we end up with the syn addition.
So in the actual mechanism, the OH plays a part, but...
In the actual mechanism, the OH plays a part. I'll pop that up in a second, and you can take a look at that within the slides. Okay. This is a very short-handed mechanism that gets to the same idea behind it. Why they didn't pick this one is probably due to some hardcore kinetic studies that proved that you needed OH minus. Okay. What's that?
I'm laughing at your term.
What? Hardcore? I guess in all fairness, I think all kinetic studies are hardcore. Okay. And we end up with our final syn addition. What is the big difference about the borane reagent in comparison to others? What was that? What do you mean positive? Okay. If we pull out all of our reagents, clear everything out. If we reacted this under mercury, or actually let's go first under our H plus and H2O. What did we get? OH at our most substituted. If we go under the two-step mercury reagent and our borohydride, what did we get? Same thing. And when we go on our boron reagent, what happens? The OH ends up going to our least substituted position. Okay. Those of you trying to memorize Markovnikov and anti-Markovnikov, I feel sorry for you. Close enough. I think I was darn close to the gave up. Okay. Questions on that? Deep breath. I know that sucks. Okay. So, if you see your boron reagent, BH3 in particular, don't. And so that's the other thing to watch out for. You'll notice the boron reagent shows up in the mercury reagent as well. Your boron has to be BH3. Okay. Your OH is going to go to your least substituted position. Your mercury reagent, your OH, is going to go to the most substituted position.
BH2 with another group.
Interesting question. If you drop in BH2 with another group, you still have with an R group here, you're still focusing on that boron acting as your electrophile, and you'll still end up shuttling the hydrogen. Okay. So there's your full-on borane mechanism, your BH3 and H2O. Notice in your very first step, the hydroxide comes in, reacts, forms your active oxygen nucleophile, which directly attacks the boron. Then you end up doing all sorts of, remember rearrangements? Yeah, you get some fun rearrangements happening to get things shuttling along, and all sorts of nasty, ugly stuff happening afterwards. By all means, have fun. If you want to look at it, take a look at the slides. Your textbook also has a similar image. It's not worth the trouble. The little shortcut I gave you works beautifully. Okay. Allegedly, the chapter reference is correct here. We're looking at chapter 19. Reduction and oxidation. You look at that reaction. Which one is it? Reduction or oxidation? How do you determine reduction and oxidation right now, according to Gen Chem? Calculate your oxidation states. When you go through and calculate your oxidation states according to general chemistry, every atom within a compound has the same formal charge, or the same oxidation state. Is that true? No. Your oxidation states will change as you move through compounds at different locations, which means if you try to use your Gen Chem rules, it's not going to work out nicely. Okay, so we need another way to go through and approach this. Looking at the transfer of electrons is a giant freaking mess. So avoid it. Okay? What we can do is go back to the origin of the names reduction and oxidation. Okay? What was the origin of the name reduction? What's that?
Removal of oxygen or reduction of...
Actually, that's an interesting interpretation. I haven't heard that one. But we'll use that in a second. There's another one. If you determine the oxidation state as you go from a +4 to a 0, what happened? You gained electrons, also known as reduction. You reduced your oxidation state. Went from a +4 to a 0. It got smaller. Okay? That's how I've heard reduction. How do we do it? Look at oxidation. Well, oxidation necessarily has to be the reverse. So as we go up, that sounds like oxidation. That didn't work. Okay? What is oxidation referencing? Oxygen. That's what oxidation is referencing. It's the reaction with oxygen. If you increase the bonds to oxygen, what have you done? You have oxidized it. If you increase oxygen, that works. Which then necessarily means when we look at reduction, which is what you were suggesting, if you reduce oxygen, you are doing a reduction. Okay, so that's a nice simple rule. What happened to the oxygens in this reaction? Okay, well, so not quite. Okay. To go through and look at this, the other thing that has to happen when we oxidize and reduce is it's also the transfer of hydrogen. By increasing the bonds to oxygen, you must also decrease hydrogen. Okay. If we look at a reduction, you are increasing hydrogen. What happened in this reaction? You increased the bonds to hydrogen, you've done a reduction. Okay. Looking at our hydrogens is a nice kind of nifty way to shorthand that. We can also reference the oxygens. For those of you moving into biochem, looking at the oxygens is easy. Hydrogens tends to be very difficult to identify because we almost always imply hydrogen, so it becomes very difficult to nail those down. So another thing that we can add in here is it's really increasing and decreasing bonds to a more electronegative element. So if we decrease the bonds to a more electronegative element, or increase them, that also applies. When we did the reduction, did we actually decrease the bonds to a more electronegative element? Yes, where is it? What about the carbon? The carbons attached to the pi bond are more electronegative than carbons that are sp3 hybridized. You actually decrease the bonds to electronegative elements here as well. Okay, we have to stop there, but I will start Wednesday with looking at labeling those reactions as reduction, oxidation, or neither. Okay, no more than 5 minutes, and then we're moving on.